one of the coolest things I've seen in a long time. All right, guys, today we're gonna dig into PEKK-A filament, specifically Thermax PEKK-A from 3DXTech, which we do sell at visionminer.com/materials. We're gonna break down what it is, why it matters, and what you can expect when printing it on something like our 22 IDEX right back there in the corner. First off, what is PEKK? PEKK, P-E-K-K. It stands for polyetherketone ketone, and it's part of the PAEK family, which is polyarylEtherKetone. And these are basically all ultra tough, really high temp polymers that are made to survive in nasty environments. Now, PEKK has 2 ketone groups per repeating unit, where PEKK only has 1. Now that little shift affects thermal behavior and crystallization, and that's very important when it comes to 3D printing because it changes how the material flows and bonds and cools. This stuff has serious mechanical strength, and even the unfilled version, like you're seeing here, very rigid, very strong, and it holds its shape under load. We'll talk about creep in just a minute, but on the 22 IDEX, we've printed brackets, fixtures, test parts that take real actual stress, which we will be getting into later in this video with the plethora of parts over here. We'll be breaking and burning and other stuff, so stay tuned. All right, so it's kind of important to note that not all PEKK is the same, right? There's PEKK-A, PEKK-C, meaning amorphous and semicrystalline, and just different companies selling different blends in 60-40, 30-70, etc. And they're all a little bit different. Today, we're only talking about 3D printing, not injection molding, not other stuff. Specifically, we're talking about the Thermax PEKK-A from 3DXTech. So C we'll save for another day. There are different grades out there. Some are more crystalline, more amorphous, and that affects the strength, the stiffness, and the thermal resistance. But really, the most important thing here is it affects how it prints. Now, PEKK-A is an amorphous blend, which is a really big deal when you're running it on the printer. It basically means less warping, better interlayer adhesion, layer welding, and it's just more forgiving thermal behavior. So basically, it plays a lot nicer with the printer. Now, on the 22 IDEX, we've had really good layer bonding, consistent surface quality, even on tall and complex parts. Now, you definitely still need a heated chamber and a super high nozzle temps, but it's manageable if your printer can handle high temp material. This part in particular was printed like that, with 0 supports, and it's very strong. I'm scared of breaking it, but I'm like, oh God, yeah, no, that's not happening. It's strong, it's very strong. It's kind of cool looking too. It is translucent. I don't know if you can see that. So that's pretty cool looking. Now, we can also talk about fatigue and creep resistance. This is one of the standout features because it holds up to long-term stress. It demonstrates basically no real creep, and it handles cyclical loads very well. So if your parts are gonna flex, vibrate, or see wear over time, you're not gonna see them stretch out or deform like with lower grade materials. As far as heat tolerance goes, PEKK-A has a glass transition temperature of about 160 Celsius, and it doesn't start melting at all until 305. So it can hold its shape in high heat environments where ABS or nylon or even polycarbonate would have pretty much already failed. So that's perfect for under the hood parts in automotive, high temp tooling, and anything that might be, sit near a heat source for long periods of time. And in addition to that, the chemical resistance is very good. It handles chemicals like a champ. Acids, bases, oils, fuels, hydrocarbons, no problem. If you're printing parts for a lab or a plant or an industrial setting where it might get exposed to the nasty stuff, PEKK-A is probably gonna hold up. Now, fire smoke toxicity. It's naturally flame retardant. We're gonna show that here in just a second. You can notice the propane torch going on. It's got the UL94 V0 FST rating, even at thin wall sections, which is especially useful if you're printing for aerospace or anything where fire safety is part of the requirement. Even without fiber fills, like carbon fiber or glass fiber, PEKK is very good when it comes to abrasion resistance. So if you're printing moving parts or sliding parts or anything that really sees repetitive contact, it's not gonna wear down quickly. Now you can also get the carbon fiber filled version, and that's supposed to be even better when it comes to wear resistance. So if you need to go even further, that's an option. But let's talk about what it takes to print PEKK-A. Basically, what we're running on the 22 IDEX is a minimum nozzle temp of 350 Celsius, a chamber temp of 100 Celsius, and a bed temperature of 140 to 160. As far as layer heights go, you know, 0.1, 0.2, 0.4. The bigger you go, the harder it gets. 0.2 is great. The nozzle size, you know, you can print with any size nozzle you want. Sticking to 0.2, 0.4, 0.6 is easy. Our profiles are set up for that. Infill is kind of cool because this can be printed 100% solid, and it's actually kind of easy. You don't see the crazy warping that you do with PEKK and some of the other more semicrystalline filaments. It behaves. It's awesome. It's really, really nice. Now, if you're gonna print this stuff, you absolutely need a full enclosure with active heating. I wouldn't want to print this stuff in under 90°C chamber. I wouldn't even go there. And you also want to try to make sure the part cools slowly, so you can set that up in the 22's end job behavior. You can actually have it, you can basically anneal some parts. The annealing for PEKK requires a hotter chamber, so you might use an oven if you choose to do that. A lot of times you probably won't need to, but that's actually a cool point with like nylons and polycarbonates and stuff like that. You can anneal it automatically right after the print job. Anyway, I digress. Layered adhesion has pretty much always been awesome for us, especially on the 22 IDEX. The bed adhesion is very, very good using our nanopolymer adhesive. Of course, our bed adhesive that we designed for PEKK and UTM, and it happens to work for everything from PLA to nylon to ABS to what have you. So really good stuff, and it's good enough that we printed this part at this angle with no supports. So the nano on the carbon fiber build plate, standard with the 22, prints like a dream. It is still important to note, I'm making this sound easy, right? Well, this is not a beginner filament. You still need a very capable machine, and it prints very reliably once you've got your setup dialed. And of course, we include a profile specifically for this 3DXTech PEKK-A on the 22 IDEX, so you'll be printing straight out of the box without much issue. All right, so that's the rundown. That's the baseline rundown. PEKK-A is a very tough, very high temperature, chemically resistant, and it's easy to print compared to PEKK or some of the other high temp materials, as long as your printer can handle the heat. On the 22 IDEX, we've had no major issues with adhesion issues or warping, and parts are super strong right off the bed like this one. So if you're building functional parts that need to last, especially in tough environments, then this is very much worth considering. With that being said, let's dive into the technical data sheet for all the engineers out there. We've got a density of 1.27 grams per cubic centimeter, tensile strength of 105 megapascals, tensile modulus of 2750 MPa, tensile elongation of 5%. I'll show that here in a second, hopefully. And flexural strength of 95 megapascals, and flexural modulus of 2,680 megapascals. The glass transition temperature is 162. The melt temperature is 305 and Celsius. These are all Celsius. And the deflection temperature, heat deflection temperature, is about 150 Celsius. And that's the max real continuous long-term use temperature. You can go a little bit higher for short periods of time, but if you're in a 145 Celsius environment, then this stuff will do pretty well for you. And it's got the flammability rating for the base resin of UL94V0 at 8 millimeters. So that's the TDS, and let's check out some parts. This is the fun part. So let's get into the practical material testing so you can see exactly what actually happens with these things in real life. I wanted to break out the UTM and just show it off a little bit and use it to show the stretching of the PEKK. It's absolutely kind of ridiculous. Okay, if you look really closely here, you'll see the notched markings moving apart from each other while the entire part is elongating. And then it finally ends up breaking right down at the bottom. On this other part, shaped more like a standard tensile bar, we get the full stretch. Look at that thing, just absolutely morphing as it goes before it finally breaks right at the top. Let me just show you those two parts that we broke. The first one, the sort of chopstick thing, if we look, oh yeah, you can see some of that stretch. Look at that, it's just cool looking. That's just neat. But then the next part, really, really cool. Okay, so here you can see it really stretched. It just all moved. You can see the little markings that I put there. And even they stretched a little bit all the way up to the end here. Absolutely cool. All right, do you guys want us to do an entire episode just showing 3D prints off under the microscope? Is this cool? You like this? Let's do it. We're gonna do it. But let me know that you want to see it in the comments below. That is amazing. So really, really, this stuff gives. So let's get into the other stuff. Let's break some parts. So I'm gonna use this vise, sort of throw back to the videos from years ago. And I'm just gonna grab one of these little chopsticks and let's see how this guy really does. All right, so it's secure. And let's just do a bend test. This is a 5mm chopstick. And I'm just gonna, oh, fascinating. We gotta look at this under the microscope too. I mean, that really is going through the layers, right? So did it end there? Maybe the layer adhesion. You don't get 100% isotropic strength, this kind of stuff. On a part this small, you kind of can because there's so much thermal mass. Oh, look at that break. Wow. Fascinating. That is, that's good layer welding. That's very good layer welding. And just a cool break. Didn't take too much force. Let's do it again. Okay. Not too bad. This one broke a little bit more sort of normally, as you can see. Very cool. Very neat. Let's do a different part. Let's do a big chopstick. Let's just show the bending. Okay, so 5mm by 5mm by however long that is. We were talking 125mm it appears to be. So if I'm just gonna hold it on the end, it's bendy. You got some give, got a little bit of give, and depending which angle I hold it at, because the layers are stacked like that from bottom to top. So if I turn it sideways, it feels the same. It's 100% infill. Slight difference. This is one of those big things in the industry where it's like the standard testing standards for like metals and ceramics or whatever, what have you, don't always really apply to FDM 3D printing because the parts aren't isotropic. You have the layers and the lines going in certain directions, and just changing the direction of your infill will affect the strength. So we need to come up with some new testing for additive for specifically FDM. If you guys got any suggestions, I know I'm asking for a lot of comments, but put them down below in the comment box because there's a lot of discussion out there, even at events like AMUG this year in Chicago and potentially Rapid in Detroit, which we will be at. Yeah, okay, so let's see how far it bends before it breaks, and then how it breaks. Oh my gosh, this is ridiculous. Oh my gosh, I'm gonna hurt my hands. So I'm gonna get those gloves, because brought them along for a reason, right? Got these leather gloves. These actually come with the 22 IDEX when you purchase in the toolkit. We include a bunch of basic tools and drivers and things like that. All right, so let's break this thing. Whoa, whoa, look at that. Oh my gosh. Ugh. That is freaking, Okay, let's check this out under the microscope. Wow, so the bend, the stretch, and then finally the catastrophic failure. It's crazy. Should we make a segment called Breaking 3D Prints? All right, and then here, let's break it even more under the microscope. Can we see the break? Let's watch the break. Okay, so we still got a few layers in there. Oh, that is crazy. Wow. Look at this. Impressive. Wow, that's pretty neat. Let me show you some parts. This part and these parts we did for some sort of bicycle company. I'm not sure exactly what they're using it for. I don't believe they could tell us or they told us. Pretty cool, really rigid, really strong. And like these ones, they printed upright like that. Very cool. This is a PEKK impeller that we did years ago. It was actually done with the Filament HT back in the day. And you can see this was PEKK-C. So you can see in there that tan color looks just like PEKK, but it's not PEKK, that's PEKK-C. And then the thin walls out here cooled at whatever rate didn't allow them to crystallize. Now you could throw this in the oven and anneal it and get that full crystallinity and that tan color. That's just a pretty neat part in PEKK from years ago. Let's check out the pressure chambers. So we printed these little guys right here and we filled them with very high pressures of compressed air until they exploded. Now, we're working on this testing and making it a little bit better so we can show you guys really well. You might have noticed we have a lot of these parts. They are our standard material sample bars with a stick on the end. We've got a bunch of them because we've got a bunch of different chemicals that we're going to be dipping them in and time-lapsing. So you'll be able to see the chemical resistance and what actually happens in different chemicals to these materials and all the other materials we carry. So again, stay tuned and subscribe. So we're gonna do a little torsion test. We got this handy dandy little doohickey here known as a digital torque adapter. So I've got a 10mm socket and an 11mm socket for these two parts. So let's start with the 10, the fabled, legendary 10mm. And then we've got it on P-top. So it should show you guys the result. All right, here we go. Let's see what happens. All right, and you see there, it just sort of sheared off. And the number we're getting is 3.2 Newton meters. Okay, interesting. Let's check it out under the microscope, see what actually happened. Oh yeah, twisting. You know, it's interesting, all those little fibers and whatnot. Very, very cool. All right, P-top once again. Slide that on there. And here we go. Woo, all right. And I'll leave this one not fully broken. That was also 3.2 Newton meters. Now that one didn't totally break. Oh, dude, it's still rigid. What? This is nuts. So you can see there the twisting very clearly. And it's off base, so a lot of it disconnected. A significant portion of it. This thing is still very rigid. There we go, I broke it off. That is cool. Ha! Very neat. Very, very neat. Okay, so let's do a little more practical testing. Let's cut it with wire cutters. So I'm just gonna take that chopstick from earlier. Let's see what happens. Ugh. Look at that. This is very, very interesting. It's almost like it's soft. Whoa. Whoa. All right, I mean, it kind of feels like a hard nylon or something like that. Interesting. All right, well, now for a lot of our favorite part of the video, we're gonna burn some stuff. So we're gonna check it out under the microscope after as well. So I will just get, just in case it likes to snap, crackle, and pop, proper safety equipment. And we've got the PEKK lighter and the propane torch. So we'll start with the PEKK lighter. And I'll just use this piece right here. Use the glove to protect the nice wooden table from drips. Let's see what happens with the timer. 5, 6, 7, 8, 9, 10. Okay, and it went out. Fascinating. Let's do that again. See if we can get it to catch fire. Oh, that's neat. Okay, it's expanded greatly. So we saw what happens with a lot of polymers where they sort of expand and get a little bit crazy looking. Oh! Okay, this microscope was a great idea. Credit to Cole for bringing in the microscope. That is insane looking. That it looks like an alien planet. But it's fully self-extinguishing. And it just smoked just a little bit. So now let's hit it with the big guns. I'll do the opposite end. Whoa, that's crazy. All right, now let's grab it and move it around. Oh yeah, look at that. That is pretty wild. Dude, but as you can see, it does not stay on fire. It very much puts itself out. It's not dripping anything like something like nylon would, which is a really big deal for aircraft interiors and cabins and stuff like that, where it needs to, if it does catch on fire, it needs to put itself out and not gas people. So, wow, fascinating. Let's see if we can do that under the microscope. Let's check this out. Here we go. this. It's one of the coolest things I've seen in a long time. Wow. Okay. So that's pretty sweet, I gotta say. And then with the gloves, it's still soft. It's still soft. It is crackling. There's a bunch of charcoal coming off of it. Now it's kind of moldable, so you could like squeeze it around, and you would probably never actually want to do this. Do not try this at home. We are professionals. There you have it. The first in a series of videos testing all these 3D printed materials. Now this is a basic test. We have a bunch of other stuff we're doing. So make sure you stay tuned and hit subscribe and leave a comment. Like this video if you liked it. Share it with your friends. And we'll be doing a lot more of these videos. And Cole will join me very soon. So hope you guys enjoyed. I hope this was informative and showed you something not only about the tech specs of the material and what it's capable of, but the practical, actual use and handling of these materials. And just, you know, let me know if you liked it. Go to visionminer.com/materials to buy this or this and a plethora of other materials. And just since I forgot earlier, let's show you what the inside looks like. Nice thick Mylar bags, and they should be dehydrated from the factory, but we do tell you just dry it before you print it because it's not worth the risk of it being wet. So there you have it. There's the material. Thank you so much for watching. Have a positive rest of your day. I'll see you on the next video.